Okay, in this video, what we're going to do is take a look at OpenGL's lighting. This is obviously extremely important in creating a fantastic-looking final masterpiece in your 3D virtual world.
It vitalizes your 3D world.
It does. Without lighting, your scene would look very bland. It would look very flat because, well, everything would be equally illuminated, and there would be no shading, so you'd get no sense of depth, and it would be very boring, and there you go.
Yes, exactly.
So obviously, lighting is important.
Yep.
Now, we don't have a lot of lights to work with inside of OpenGL. It's not like if you were working in 3D applications like 3ds Max or Maya, where you can go and put hundreds of lights in a scene and just let the rendering engine worry about calculating all of those lights. For the most part, yeah, we're limited by the video card. And in most cases, it's 8 lights that we can work with.
But typically, this is not really a limitation, simply because in your application, in your 3D engine, you would say, I can see 6 lights, and you would only have those 6 lights visible. And then if you move to another section of, say, your game engine or your level, you would make those visible, and then those calculations would begin.
Exactly.
So you do have to work at it. I mean, it would be nice if you could have 100.
Involved.
Yeah, but there is some planning involved. If you think about it, there are ways to reduce it, so you only really need at most 8 lights at any particular point.
Exactly. Now, there's a very, very important concept that you have to understand about lighting inside of OpenGL, and that is it is per vertex lighting.
As opposed to per pixel lighting.
Per pixel lighting, which we can do.
Yes, we can.
But in order to do per pixel lighting, you've got to create your own custom shaders.
Right.
And this is something we're going to take a look at when we get into VTM number 2, covering OpenGL. So right now, we are limited to just per vertex lighting. And so this makes you guys have to think even more about the illumination of your objects. You have to start thinking about things like the detail of the geometry itself.
Right.
So, as a matter of fact, if we can go and jump over real quick to our whiteboard, I'll show you guys what we're talking about. So, if we were to come in here, please just bear with my incredible drawing skills. So, oh yeah.
Then go.
Yeah, that's nice. And so we have some
surface
quad strip here. And we've got
3 quads.
Vertices all the way around. And then we have a spotlight that's shining down and hitting this area right here. Well, basically, here's what's happened. Here's what's going on. You first must enable lighting, just like we did with textures when we took a look at how to do textures inside of OpenGL. We enable lighting, and now lighting calculations take place. Then we must go through and enable the lights that we want to utilize inside our scene. And then we can set various parameters, etc. Then what happens is during the calculation of the color for each of your vertices, because remember there's a texture that's probably applied or some sort of color, and then there is the light that's hitting it, and it's a combination of these two things that's going to give us the final color that we're going to see in our viewport. So what happens is we go through each vertex internally. The engine takes care of this. It says how much lighting is striking this guy right now. None. So as far as lighting is concerned, there is none. So, you know, it's just our regular color, but since lighting is being involved, it's 0, and we multiply our texture color by our light color, and what do we get? 0. So now we're black. Fantastic. So now we slide over here to this guy. Again, what lighting is hitting it? Well, right now, look where our light is. Our light's striking this center polygon. So up here is 0. So multiply 0 by the texture color, 0. 0. 0. And you can see how all the way around they are all 0.
And internally, when it's actually going to shade your surface, it's going to blend between each of those, the colors of those vertices.
Absolutely. So we're blending from 0 to 0. So this entire thing right here
is black.
Yep. Okay.
So even if you did have a texture, it'd be multiplied by black, which is 0, and your final surface would end up being black.
Precisely. Now, what if I was to take my spotlight that's shining down on this polygon and open up its cone angle just enough so that we cover these vertices? Well, now there's several factors involved in the calculation of what's going on. Let's say that we are completely intense in this area right here, and then we begin to kind of fall off as we work our way out, which this is the exponent. We'll be talking about that in just a little while. So our value begins to diminish. Well, let's say that by the time we get to these vertices out here, what we're looking at is something like 0.8, 0.8, and 0.8. Now, Joel, why am I doing this in like a vector format?
Basically, we have an R, G, and B component that goes between 0 and 1, with 1 being full intensity. So if it was 1, 1, 1, we'd get white.
And if we get 1, 0, 0?
We get 1. What, when you, 100, I'm sorry, red.
I promise you it's not a trick question. I wanted to get you to say some color other than white or black so that people realize, our light obviously we can have colored lights.
Yes, we can have colored lights.
And so here we are. We're representing, I guess you could say, a grayscale color right now, a gray color.
A very bright gray.
And it's a very bright, that's right. So now let's go back through and we're going to do our vertex pass again, where we do all of the calculations on how much intensity each of these vertices. Now, of course, when we calculate a vertex, the engine looks around to see what lights are striking it. So it's not just
one light. It takes into account every single light that's currently enabled. Remember, at the very start of your OpenGL state machine, every single light is already there. Every single light that you have is there.
Explain that slowly. That's right, guys. When you first start OpenGL, your lights are all there. Your maximum number of lights.
Let's say you have 8 lights.
You have all 8 lights
would be there, but they're all disabled by default.
That's right. So, and lighting itself, the lighting calculations, that is disabled as well.
Right, so even if you enabled one of those lights, until you actually enabled lighting as a whole, they still wouldn't do anything.
Precisely. So in this particular case, as we do the vertex pass and we go through and calculate the intensity of light on each vertex, we would end up with this one being 0.8, 0.8, 0.8. We come out over here, and of course this guy is still 0, this guy down here is 0, and this guy is also still 0.8, 0.8, and 0.8. There's a comma there, really.
Yeah.
So what ends up happening? Well, take a look at this. We start out with pitch black.
Right.
And it blends, it interpolates from black to, and we start to get lighter, lighter, and lighter until we reach this 0.8 value.
Right, now, so we get as a smooth gradient from where our color is 0.8 to where our color is black.
That's right. And check it out. Here, we're going to look at it right here. So it looks kind of like this. That's getting lighter, really. Now let me draw it in a square form, like such. There we go. Now,
it is smooth.
There we go. That is smooth. But check this out. Look at again, we're looking from a top view right now. Look at the curvature of the light created based off of my cone.
So theoretically, we should be getting sort of a circular shape inside of that shaded area.
So right here it should be dark. I mean, it should technically be black, right? And then we get our really light color here. Well, the problem is we don't have enough detail in the geometry. We don't have enough vertices.
Right.
Since it is per vertex lighting, if we wanted to represent in our viewport this nice edge over here, right? As a matter of fact, not only this nice edge, but the nice fall off that you would get if we went from super intense right here to falling all the way off to black.
Yeah.
Then what you're going to need is a lot of vertices. So we're going to need a lot more detail. So it would be like detail, 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 detail.
And then you get into the point where you go, do I want more detail or do I want better looking stuff? I mean, or do I want less good looking things?
Yeah, I mean, it comes down to we're trying to create real-time applications.
Right.
At what point do we want to start sacrificing the word real-time just so that we can make our lighting look real good? And there is a trade-off. And it really does.
Huge trade-off.
It really does come down to experimenting and playing with it and getting what you think looks nice.
Right.
And there you go.
And a lot of times you'll find that with a very small number of vertices, you can get the look you're looking for.
That's right. Now, there is some good news, and that is we're not limited to only working with per vertex lighting. We can work with per pixel lighting.
As we mentioned a second ago.
And this is, I guess you could say, per pixel shading, and this gets into you must be able to create your own custom shaders, which we're going to look at, like I said, in VTM number 2. But in that case, then you can take into account every single pixel that is getting rendered. Okay? So the final thing just that I want to show real quick is that here we are. What do we have here?
Another
2 overlapping lights. So this vertex is receiving illumination from 2 different lights, and this guy could be 0.8, 0.8, 0.8, and this one over here could be 0.3, 0.3, 0.3, whatever it may be. And then in a second, we're going to take a look at a lighting model where for each vertex, we're calculating an intensity based off of all the lights that are striking. So here we are in a situation where we do have 2 lights striking a vertex.
And what ends up happening is you don't have values that go above. That's called high dynamic range stuff.
Right.
And by default, we do not have that. It basically clamps it to 1. So the max value you get is 1.
Exactly. So this is just a quick look of, I guess you could say, what's happening internally. The bottom line is to remember is this. You enable lighting.
Right.
So once it's turned on, now you go in there and you can enable one of up to 8 lights. I mean, perhaps more or less, depending on your video card. And then you can set where the light's pointing and all sorts of fantastic parameters, which we're going to look at in just a few minutes. But now what happens is each time we go to draw things, we go to do that refresh, the engine's going to have to walk through each vertex, do a calculation to determine how much lighting, what's the light intensity on that vertex, and then multiply that information by your color information, your texture, whatever it may be.
Your material, essentially.
Your material. And then it's going to need to calculate the interpolation between the values calculated at each of the vertices, vertices, and then you get your shading on your polygon. So that is a big look, the big picture.
Right.
Yeah. So there you go.
So if we go back into here, let's go ahead and go to the next slide and look at the Phong lighting model in a little bit more detail. Essentially, you already know that everything that's here.
We got to throw this out quick.
Yeah, sure.
He's like, he just snuck the word Phong lighting model in there. Phong.
Have we not mentioned it before?
No, I don't think so. Yeah.
Okay.
So
basically, inside of OpenGL, we utilize the Phong lighting model. There are other lighting models.
Blend, anisotropic.
Et cetera, et cetera. There's a whole bunch of them that have been created or invented or however you want to say it.
Exactly.
So basically, inside of OpenGL, what's implemented internally is kind of a Phong lighting model that we have. And this is basically the formula that's used internally to calculate this. So basically, we have at the very left here our total intensity, if you will.
Which is what we were just talking about a second ago when I showed the two lights overlapping that single vertex.
Right.
What's the total intensity that we're going to be
Exactly. Basically, it loops through every single vertex and performs this formula on every single vertex to calculate the total intensity at that particular vertex.
That's right. Now, this is really funny because this looks super scary.
Yes, it does.
And the first thing you may think is, I'm not really that hot with math, and now am I not going to be able to illuminate my scene? Yes, you'll be able to illuminate your scene just fine.
It's actually really, really simple.
Yeah, you're going to find that it's really easy. But having an understanding of what happens at a lower level makes you just a bit more dangerous when it comes to setting the various parameters that show up in this formula
right because
here.
You can specify like this constant here, the constant ambience, et cetera, et cetera. You can set that inside of OpenGL. The only thing is you're not actually implementing this particular function or this formula by hand. But when you do, as we said before, our shaders, if you create your own custom shaders,
then you
will have to know how this works. So it's a good idea to start familiarizing yourself with how it works.
Absolutely. So you can see where that is really important.
Exactly. So before we actually look at this a little bit more.
One more thing I'll throw out real quick is, plus having an understanding of what happens in regards to calculating the lighting makes you a bit more knowledgeable when it comes to troubleshooting when let's see all of a sudden your surfaces are black.
Right.
You're like,
I mean, that can be a
huge
thing.
Absolutely.
I mean, if you understand what's going on, you can very quickly debug your scenes.
That's
or at least hopefully. So a little, before we're looking at this, let's look at this diagram down here. You'll notice we have the various vectors here is L, N, V, and R. So what are these vectors?
Well, first let me say this.
Okay.
We have that line running along the bottom, with parallel with the bottom of your monitor.
Yep.
That is a cross-section of a polygon.
Right. Consider this area just a polygon.
That's right. And then the N, this is our normal.
Right. And that brings up another very, very important thing. When we start dealing with lighting, we must have a normal. And we'll be able to specify this. We'll show you how.
And we'll talk about it in just a second.
Yeah. So then we have this other vector that shoots towards the light, from the vertex towards the light. And then we have a reflected vector that reflects off of the normal vector from the light vector. So this is the reflected light.
That's right.
And then our final vector is our vector V, which is from our vertex to our camera. Exactly. Right. So with these four
we don't really have a camera. So it's right back to the
model, right.
Yeah.
So how does this start out? Basically, we have our ambient color, which is basically the color that illuminates our entire scene. So we have
a scene-wide thing.
Right. We have our I ambient. Our K ambient is something that is per material. And again, this is run at every single vertex, so each one can be different. So each of these Ks is a constant. And then we add on to that our summation, which basically loops through every single light and adds the intensity of each of those lights.
Again, like we saw just a second ago, two lights overlapping one vertex. So obviously the intensity is going to be different with two lights hitting it as opposed to just one.
Exactly.
So we need to loop through all of them.
Exactly. And then we have the intensity of our light. Notice I. We define our I right here, which is looping through every single light. And then we multiply the intensity of that light by our K diffuse, which is our material property, the diffuse property of our material. And we multiply that by the dot product of our normal and our light vector, which essentially means if the light is right above the normal of our vertex, the intensity of that point is going to be at max.
That's right. Well, think back to how dot product works.
Mm-hmm.
We can end up with a value of 1 or higher.
Right.
And then, of course, as the light swings all the way around, let's go counterclockwise,
right.
all the way to the far left-hand side. Yeah, now we're perpendicular, so what would we have? A value of 0.
Right.
And think about it.
So no intensity there.
If you took a flashlight and shined it sideways on a piece of paper,
mm-hmm.
what kind of illumination are you going to get on the top of the piece of paper? None.
Right. And then we add that calculated value to our specular component. Because with the Phong lighting model, what's cool about that is it allows us to do things like have a specular highlight.
That's
This
right.
can be really, really important if we're trying to simulate things like metallic objects. If we want that little bit of specular highlight. And this comes down to the same thing. If you have a sphere that has only a few faces on it and you try to calculate the specular highlight, it's per vertex. So the specular highlight is going to be really unclear. So you may have to increase the detail of your sphere
mm-hmm.
before you can actually see the specular highlight nicely.
Exactly.
So we take the specular highlight of our particular material and multiply that by the dot product of our vector that goes to our camera and our reflected vector, R. And take the dot product of that to the power of our shiny, basically a shiny constant that we can also define inside of OpenGL that
mm-hmm.
specifies how shiny our particular object is, and multiply that with our specular component. And so we go through every single light, adding all this information together, and finally pumping that back into our vertex.
That's right.
And there you go.
That's right. Now, the normal is generally something that you're going to bring in from some 3D application where you're going to create your models.
Mm-hmm.
I mean, let's be honest. You're not going to want to sit down with the OpenGL library and create a complete character or a complete city
mm-hmm.
through code.
Right.
I mean, that would, and then define all of the normals, and that would just be a pain.
Right.
So usually,
some people do it, but I don't recommend it.
No. It was just going to take a lot of time.
Yep.
Generally, you're
Unnecessary
going to
time.
work inside some 3D application,
mm-hmm.
put your stuff together, export it out, import it into your own application that's utilizing OpenGL, and at that point, you should be bringing in all of your normal information,
exactly,
etc. But we do have the ability to specify that. As a matter of fact, if we go to the next slide now, let's take a look at some of the calls that are required to utilize lighting.
Right, basically the procedure you need before you can get lighting set up inside of OpenGL.
That's right. Well, the most important one, just
mm-hmm.
like as you guys saw with
textures,
because we need it GL enable for that.
Right.
We need it for lighting. So GL enable, GL lighting is going to basically fire up the lighting engine.
It's going to turn on the light switch.
That's right. So that lighting calculations are now going to
be calculated.
That's right. Take effect.
And the next thing is, of course, as we said, we have multiple lights that we can have
that are
in our
all
particular
there
scene.
by default,
mm-hmm.
period. They are there, all of them.
But we need to start enabling whichever ones we want. So if we want to enable light 0, 1, and 2, we would actually go in and have 3 separate calls to GL enable that enables each of those lights.
That's right.
And you'll notice I'm passing a constant here. You can't just say GL enable 0. That just doesn't work. We have our GL underscore light followed by 0, 1, 2, 3, etc. that allows us to enable those specific lights.
That's right.
And we can use a GL get call that will allow us to get how many lights are available inside of whatever video card we're currently running on. And you'll notice the class that we create in the next lesson will actually show you how to do that.
Right.
And then we have our GL normal call.
Ooh, important.
Very, very
3F,
important.
it could be 3D, but we need to specify what the normal is going to be. And because it's a state machine,
mm-hmm.
keep in mind when you do a GL normal and you specify what that normal is going to be,
right.
you make a polygon, you make another polygon, and that new polygon has the same normal. If you make another one, same thing. So we need to continue specifying before creating the polygon what the normal is going to be.
Exactly.
And you see how it takes in a vector. We've got an X, a Y, and a Z component.
mm-hmm.
If we jump back over to the whiteboard real quick, I can show you guys how with our really simple cube, something like this would be real easy. So let me see if I can give you guys
Right, and again, as we were saying, if you have a more complex 3D character that's facing in every direction, you have smooth hands and articulate fingers, calculating the normals can be quite difficult and time-intensive, especially.
Precisely.
So you may just want to have it calculate inside of an external application.
So here we are with X, Y, and Z, as you guys can see. So if we were about to create this particular polygon right there, we would go ahead and set the normal
mm-hmm.
as, this is what we would pass it. We would simply tell it it's going to be 1, 0, 0. And that's going to set our normal so that, well, we're pointing along the x-axis.
Exactly.
Like such.
So remember, it's just the perpendicular to that face.
That's right. So 0, 0, 1, and of course up here it'd be 0, 1, 0. Now, of course, if we had something that was slanted off at some funny angle, then there's some very simple mathematics that you can use to calculate that normal.
Because, right, as we looked at in the vector
Yeah, I mean,
class.
The bottom line is you've got a vector and you've got another vector, and then just
let's put an arrow at the end just to make it. Okay. Okay.
Donk, 90 degrees.
Right.
Ringing bells.
Yes,
But
it
anyway,
does.
so we can go in there and we can calculate our own vectors. But the deal is this. Do you really want to go through doing something like this? I mean, once you...
Calculating the cross product for every single surface.
Yeah.
When you have 3,000 at least surfaces for every single character.
You're now adding a lot of overhead.
Right.
That, is it really necessary? Just keep that in mind. So anyways, I just wanted to show you guys real quickly that coming up with this is easy. But let me go ahead and just reiterate one last thing. Again, when you set that GL normal, okay, and if you don't set it again, and we go to create this polygon right here, and it's still set to this, what are we going to end up with as our normal?
Right, we're going to have the same vertex, normal that goes in the
Exactly.
x-axis.
So now when lighting goes to calculate, we're going to have all sorts of problems.
Right, and another thing to keep in mind is if that x-axis face here, and the vector was going in the opposite direction, what would end up happening is your surface would be black. Because if the normal is shooting in the opposite direction...
You're not going to get any lighting on that side right
exactly.
there. So, yeah, that's very important to keep in mind. What he's talking about is if it's coming in this way,
right,
as opposed... So it's going that way as opposed to that way.
Right, and then what you'll get is something that won't work.
That's right. Okay, so let's go ahead and jump back over. I think they have a decent understanding of that.
Yep.
Okay, so
finally,
now that
once you have everything set up, your light is enabled, your lighting is enabled, you've created your normal. How do we set up the properties for each of our lights? And basically for that, we have our GL light F, which allows us to specify which light we want to modify, and the parameter name that we want to modify, and what we want to set it to.
So we could do something like GL light F, and then tell it GL underscore light 0 or light 1, comma, and then what parameter name. And below you can see a list of the parameter names that are available to us. We can specify the GL ambient or GL diffuse, where we could tell it like it's going to be like it's going to be red, so 100. And sorry about that. Joel had a very interesting spider on him. It got my attention real quick. And so anyways, we could specify these values. So we specify it would be GL diffuse, and then the next argument would be 1, 0, 0.
Right.
That's what we wanted to send it.
Exactly. And then, of course, we have our scalar values as well that we can just simply specify. And like we were talking about before, we have our GL spot exponent that allows us to specify...
Yeah, if you shine a flashlight straight down on your desk or something, as you work your way out to the outer edge of what is illuminated, you'll notice that the intensity begins to fall off. And this is the exponent that allows us to control this, which does bring up one more very important thing in regards to fall off, and that is our attenuation of the light.
Right.
In the real world, if we were to take a flashlight, walk outside at night and illuminate it, we may be able to...
Maybe 3 feet in front of you.
Or we may be able to lightly illuminate a house across the road, right? If it's pitch black
Very
outside.
lightly.
Very light. But if you were to put a piece of paper right in front of that light, that's going to be really, really bright. Right in front of your flashlight. So the light intensity is falling off over distance.
Right.
And we have the...
Like in the real world, you never have something that can shine 3 miles of the same
intensity.
Brightness. It's impossible.
That would not be cool. Actually, it could be.
It could be
laser.
Cool. Exactly.
So, anyways, we do have a few different things that allow us to control that. We've got GL constant, linear, and quadratic attenuation parameters that we can set, and these will determine how that fall off or attenuation is going to be calculated for the light. If we can, real quick, Joel, let's go ahead and jump back over to the whiteboard, and let me see if I can just clear you guys off a little bit of space, because this is scary looking.
Yeah, it is.
Hey.
Nah, it's okay.
It's beautiful.
It's cool. All right, it's beautiful.
Now it's beautiful. It's a masterpiece. So here's a very simple formula. 1 over... I'm trying to make it straight. Now, we have a few different constants. So we've got K1. And in a second, I'll explain what each of these K's
Remember,
are.
K is just a constant.
That's right. So now 2. We've got K2 times D. Hang tight. 1 second. Let me get the formula in.
These are all constants.
And then K, with the exception of D, of course. And then we've got K3 times D square.
Right.
Now, you may have seen this formula laid out in several different ways.
Right.
This one works really well for us for explaining how exactly we're going to calculate our attenuation. So first thing I'd like to do is let's create a little legend over here. So K1 is going to be...
How much our constant, right.
K2.
Our constant attenuation.
Is going to be linear.
So our linear attenuation.
And then finally K3 going to be quadratic.
And remember, D is just the distance from whichever vertex we're currently calculating to the light.
That's right. So, yeah, exactly. So now, with this, we can easily determine exactly how the light's going to fall off. As a matter of fact, if I kind of cruise down here and make you guys a really rough-looking chart again. There we go. What we end up with, oh yeah, let me do this too. D is going to be distance.
Okay.
Because that's really important. And that, as Joel was just saying a second ago, is the distance between the pixel and then the light source itself.
Or vertex.
But that's what I mean, the vertex, excuse me. You get into teaching so many 3D applications.
Yeah, I know.
So vertex, light, so this is our distance right here. Okay. So now, basically, this is going to represent our intensity, and this is going to represent our distance.
So our x-axis is our distance, our y-axis is our intensity.
Precisely. So if we were to come in here and specify just a constant, here is what it would look like.
That's an amazingly straight line.
Thank you. I reached all the way across, Joel, to grab that shift key. So this right here basically says we have this intensity that as we get further and further and further
away from the light,
it's still going to be the same intensity as it was if we were just right up on it.
And this is the default for most lights.
It is. Now, again, are we going to get a realistic-looking lighting in our scene if we use constant for everything?
No. But this is a good way to simulate some sort of global scene illumination, like the sun. You typically want to illuminate your entire scene with like a light, slightly yellow light. That's okay. With this, it would work perfectly.
Would work great. That's right. Now, if we wanted to define constant, now the K1, K2, K3, as you guys just saw the parameters, we can specify these, which is awesome. So in this particular case, what we'd want to do with a constant would be take K1, set it to a value of 1, take K2, set it to 0, and K3 and set it to 0. And the reason we set K2 and K3 to 0 is because 0 multiplied by distance is just simply going to give us 0, and same thing over here.
So basically we're taking distance out of the equation.
That's entirely. Right. So we end up with just K1, and that is just a value of 1. And 1 over 1.
Or 1 over K1, yeah.
Or, which is just 1.
Exactly.
And then that means we have a constant value. So let's go ahead and just
specify that's constant.
Yeah. So then if I wanted to do a linear fall-off, so now with linear, what is it going to look like? Well, we'll start out with our attenuation, our intensity, and then we're going to begin to fall off. I mean, start falling off immediately, but it slowly gets slower. But it never gets to 0, right?
Right.
So it just kind of goes and goes and goes and goes. And
so it's just basically 1 over D.
That's right. And to get that, what we end up with is K1 equals 0.
Ah, beat you to it.
K2 equals 1. And K3 equals 0. I don't know. That was close. And then this right here is going to give us linear. So I'll just write LIN.
That turns into 1 over D.
Exactly. Now, if we wanted to mimic real-world lighting, we'd need to use quadratic. But this generally doesn't look good.
No.
Because it really comes down to your items being built to the scale of the world and all of that. I mean, that gets kind of involved in getting it to look just right.
Right, because you may have to really crank up the intensity of your lights.
You would have to. You really would.
And typically it just works better, and bottom line is you want it to look good. So whatever works. And typically linear works a lot, really well.
So in this case, we'd have K1 equal to 0, K2 equals to 0, allowing us to take just regular distance out.
K3 is 1.
And then put K3 as 1. Yeah. And this allows us to use distance squared. So 1 over distance squared. So basically, now this is going to be quadratic. And this allows us to take light that's going to do something like this. Well, not ran to the ground, but you get we never go to 0, but it's like pink, like that.
Yeah.
We fall off a whole lot faster.
Right.
Now, obviously, if we needed for some really crazy reason to come in here and have light that fell off even faster than quadratic, we could do things like set K1 to a value of 1 and K3 to a value of 1, and now you're going to get a fall off that's even faster.
Yeah.
So there you go. That's just a really quick look at fall off, or basically attenuation of light as it travels over distance.
Yeah.
Now, Joel mentioned something else that we haven't really talked about. So before we even leave this slide, let's talk about it.
All right.
What kind of lights do we have available to use?
We basically, I mean, in a 3D application, if you're used to some 3D applications.
Like spotlights, point lights, directional lights,
so what's
area
a point
lights.
Light? A point light is like the sun. It shoots light in every direction.
I'll be quiet for a minute.
All right. A directional light is something that just shoots light constantly in one direction.
Okay,
it's not really emitted.
No
it can't be emitted from a point.
It's like it's coming from a plane that's infinitely large.
An infinite plane.
Infinitely far away.
Right.
Shooting light that the rays are parallel to one another.
Exactly.
So if you wanted to reproduce like sunlight, you'd want to do like a directional light, because in that particular case, the light rays are traveling right. They're parallel to one another because our sun is so huge.
Right. It's so far away from us.
So far away.
Right.
Well, the combination of two gives us these
parallel lines.
Lights. Yeah. So we have directional, and we have I guess you could say a spotlight. It's just a positional light, where we can, through basically setting more or less its cone angle, determine is it going to act like a point light by setting it to like 180 degrees, or is it going to be just like a regular spotlight by opening it up to like a little 40-degree light or something. You get the idea.
Yeah, and you'll notice, if we go back to our slide, if you don't mind.
Yeah, absolutely.
You'll notice that we don't have a GL light type property for our GL light app.
Because they're all the same thing.
Well, no. Well, sort of, kind of.
Yeah.
In a way, what we do is, to specify what kind of light we're working with, we pass the light type inside of GL position.
Right.
When you pass to GL light FV, the parameter for GL position, you would pass X, Y, and Z, which would be the position, and then a final W component, if you will,
1.
which is 0 or 1, specifying whether it's a positional light or a directional light.
That's right.
0 being directional, 1 being positional.
Still just the same light.
Yeah, I know. It's still the same light.
Right.
And if you wanted to simulate a point light, because we only have 2 light types, what if we wanted to do a spotlight? We could set the cutoff, which is basically the cone angle, to like 45 degrees if we wanted it to be 45 degrees.
Now it's like a spotlight.
Right. If you wanted to set it to a point light, which emitted all around you, it'd simply be 180 degrees.
Exactly. Now it's like your light bulb that you screw into a light fixture. Cool.
So I think that's pretty much everything.
Okay, again, this was just meant to be a quick introduction to lighting.
Well, there's one other thing.
Let's throw it out.
All right. So we have our GL position, our GL spot position. One thing that's very important to remember is, say you have a light in your scene and you rotate the camera around, you're going to reinitialize your lights every pass through your loop.
Okay.
So basically you have to say, all right, set GL light FV, the position and the spot direction on every single loop, so it knows where it is. Because if you move the camera around and it's in the old coordinate space, it's going to be somewhere completely different.
Right.
So you need to reinitialize and say, this is where I want the light to be.
That's right.
But otherwise, as you can see, it's really simple to set up lighting.
And in this next video, what we're going to do is create a very simple light class that's going to make working with lights
even simpler.
Really, really easy.
Yep.
And then you can just bring that class into your own applications.
Right.
All right. So there we go. So that's going to wrap up this video, and let's go ahead and get started on working on that light class.